Hey, what's up, you amazing hackers? Hope you're all doing well today. I'd like to go over an article I found from AppCheck that says Beyond the Owasp Top 10 Chicken Bits, Pollution and Greedy Matches. Now, this article was posted on December 16th of 2022, so some things might have changed by now, but I like the outline of this article. It talks about the Owasp Top 10, and we're going to read it for you, of course, but it also talks about why the Owasp Top 10 was never meant to be a comprehensive resource. Let's get into it, shall we? So the Owasp Top 10 is a fantastic resource for web application developers and security engineers. Other top 10s exist, by the way, mobile top 10, IoT top 10, and of course the API top 10. But those are all resources great to help us. It helps raise the profile of web application security and other types, of course, promoting greater security awareness amongst and enabling conversations between developers and managers by providing an easily digestible summary of common risks. It outlines the top 10 web application security risks facing most organizations, containing well-known examples such as cross-site scripting. Now remember, this was before the new top 10 came out, so XSS was still its own separate entity there. The selection of the top 10 vulnerabilities is performed as objectively as possible, using calculations based on the Owasp risk rating methodology, picked according to the vulnerabilities' typical exploitability, prevalence, detectability, and impact during observed or reported instances. The Owasp Top 10 has steadily embedded itself within the industry to become adopted as the de facto application security standard for smaller organizations and is a common frame of reference within many web application security programs. For most, the Owasp Top 10 is a great start on the application security journey. However, the Owasp Top 10 is often criticized for being too narrow in scope and for neglecting the long tail of other security risks. The fear among some is that if controls and measures such as security training cover only vulnerabilities listed in the Owasp Top 10 and go no further, then an organization may consider web application security to be mission complete, despite the vulnerabilities covered representing just a tiny fraction of those observed. The criticism is largely unwarranted given that the Top 10 project is not designed to be comprehensive or prescriptive. The Owasp Foundation produce an application security verification standard if a true standard is required, but rather to stimulate discussion and awareness of those security risks. So what else is out there? Best practice advice from Owasp and others is for software development teams and managers to create an application security program that is compatible with the organization's culture and technology. That means looking beyond the Owasp Top 10 when considering web application security. Even severe software weaknesses may present a serious risk if there are no threat agents in a position to perform the necessary attack, or the business impact is negligible for the assets involved. And conversely, there may be risk that an organization has not considered that provide critical threats to the web estate. So, in the interest of highlighting other potential risks to an organization's web estate and why it pays to look beyond just the Owasp Top 10 coverage when making decisions on security tool and vendor selection, we'll pick a few critical, interesting, or just plain bizarre vulnerabilities not included in the Owasp Top 10 and see how they could impact you. Many of these vulnerabilities arise from delving into the Owasp project, drawing on top 10 release candidates to see other risks proposed for inclusion, but that didn't make the final cut during vote, as well as current Owasp list of alternative risks to consider and personal experience. Many of these risks will be referenced by their CWE designation, or Common Weakness Enumeration. A curated list of over 800 software and hardware weaknesses types created via community initiative aimed at creating specific and succinct definitions that capture the specific effects, behaviors, exploit mechanisms, and implementation details of vulnerabilities observed in the wild. Starting with chicken bits, more formally known as inclusion of undocumented feature, CWE 1242 refers to the inclusion of undocumented features that can provide weaknesses such as privileged access, a form of security through obscurity. The name comes from historical use of so-called chicken bits on hardware chips that can be used to disable certain functional security features, facilitate quick identification and isolation of faulty components, or disable features that negatively affect performance. This is a big one, by the way. Documentation in companies is it's usually a problem because, of course, you want to spend time creating, testing, and pushing to production, not just documenting things. It can take a long time to properly document these things, and pushing undocumented features to production might lead to security weaknesses now, but especially also in the future, where new things might be implemented and there hasn't been taken proper into account that ghost features exist. Now, in web application security terms, a surprisingly common weakness or anti-pattern seen is to faux developers to add in secret methods such as undocumented cookies that, when received, enabled or disabled certain behavior. The intention by developers is to use these themselves only, and that since these secret cookies are undocumented, those outside the business will not be aware of them. However, if internal documentation is leaked, employees leave the business with ill will, or the cookie accidentally set, then an attacker can exploit these chicken bits to gain unauthorized access to systems or features. Some of these things can, for example, be developer backdoors that might be in the system. Not just cookies, but other ways to enable backdoors that weren't thought about. For example, there might be a feature to set a user to admin, and that feature might only be available in the test environment, but accidentally get put to production. And if nobody's aware of that, that can produce big problems, of course. It is critical that if any such features are added during development, they are removed before reaching production, of course. Next up, we move to parameter pollution. CWE 235, known as HTTP parameter pollution, is a class of vulnerabilities based on the inconsistent ways in which systems, services, hardware, and software handle cases in which they receive multiple parameters that have the same name but different values. So, for example, if I have username equals Wesley and then I add and username equals admin, it might try to log me in with my credentials from Wesley, but a second system might look at that second parameter username and might take admin as the person it's logging me into. Very simple example. I know there are quite a few holes in it, but just to imagine, that's what parameter pollution looks like. Variants can include multiple cookies with the same name, multiple post variables, or URL query string parameters with the same name. Despite the RFCs generally defining expected behavior in these instances, failure to adequately follow RFCs when implementing systems can lead to inconsistent or anonymous behavior. In the following examples, the parameter ID is set twice to both 123 and 321, and as we can see, it's going to log us in as the first user, but then use the second user for a simple IDOR attack. The most robust defense for parameter pollution is to actively validate the number of instances of a parameter and reject the request entirely if any parameters are duplicated. If this is not feasible, duplicated parameters should be removed by the first processor of the request to ensure that all subsequent processors utilize the same parameter value, meaning that as soon as a request comes in, all duplicate values should be stripped. Overly permissive regexes. Classified as CWE 185, incorrect regular expressions, this vulnerability relates to a generally broad class of regular expression vulnerabilities. Regular expressions are incredibly powerful, but unless carefully written, They may not evaluate strings during comparisons as intended. Potential flaws include inability to handle variations, including character case, word boundaries, and special characters, or performing overly quote-unquote greedy matches. A common example seen in web applications is when developers attempt to whitelist certain domains for access to a product or services using irregular expressions, such as seen on screen right now. I'll zoom in a little bit so it's a little bit more clear as well. That's not it. There we go. So we can see if preg match, so that's a regular expression matches, requester.com, and this might introduce vulnerabilities because the intention is to match requester.com and all of its subdomains, which looks reasonable at first, but the problem here is that an attacker can register the domain attacker-request.com or request.com.attacker.com, which are both valid. That is an example of an overly greedy regular expression. It is critical that any regular expression used for any security-related purposes are as simple as possible, since complex expressions are more error-prone, and carefully reviewed so that all wildcard characters are escaped. The pattern is anchored and tested to ensure that it not only matches the expected values, but also rejects other values. Next up, we move to Untrusted Spheres, and that's going to be the last one I'm going to read for you guys, and then I'm going to link the article in the description below. There's an increasing use of third-party components, such as JavaScript libraries and Node.js modules, within our code to provide standard functionality and service interaction. Increasingly, developers are opting to load these client-side libraries directly from a third-party CDN, content delivery network, or similar, rather than including them in their own codebase. To see why this can lead to a vulnerability, consider if our login web page included a JavaScript visitor tracking widget from a third-party domain. So as you can see, we have external domain.example.com with a tracking widget. If an attacker compromised the external domain, or the domain itself is operated by an attacker, they could add malicious functionality to the script and our page would duly execute it, allowing an attacker to perform attacks such as cross-site scripting. For example, user login information could be easily stolen with a single line added to the tracking page itself. This vulnerability pattern has the ID CWE829 and is known as inclusion of functionality from untrusted control sphere. This vulnerability can be eliminated by only including components from within the codebase that have been validated to ensure their correctness and authenticity. However, this may not be a suitable solution for the modern web. An alternative is to use the Sub-Resource Integrity SRE. SRE is a security feature which enables the browser to validate the resources they fetch are delivered without unexpected manipulation, by comparing a cryptographic hash of that resource and rejecting it if the hashes do not match. So basically the server has a hash in memory, it hashes the resource that it's taking in, and if the hashes is not the same, then it rejects that resource. That's a very basic idea of how that works. Note that when using SRE, it is critical that the hash is not dynamically calculated by the application, but is instead intentionally controlled by the developer, and any change to the remote resource which causes its hash to change be considered as a potential attack there. So we have some figures there as a comparison. Now we have a few more examples. I'm not gonna go over them all because we could be here for a little bit more, although there are not that many more. You know what, let's do all of them because that way at least we have an idea. Let's talk about salts and hashes as well. Sometimes vulnerabilities don't have to be new or cutting edge to present serious risks to a web application's security. Data breaches continue to show that companies get it wrong with the storing of customer passwords over and over again. Logged in CWE as CWE922 This is classified as insecure storage of sensitive information. It made it onto the Owasp top 10 list in 2007, but has since dropped out of the top 10 as new vulnerabilities have been voted to be greater threats. However, given the continued and ongoing history of data breaches and theft of customer passwords, it seems as though many developers are still not storing passwords securely. Made it back onto the new Owasp list, by the way. The secure storage of passwords really warrants an entire article in its own right, and there are subtle details that need bearing in mind, but in general, a strong solution would involve storing the password hashed rather than in plain text or encrypted, using a strong modern hashing algorithm, not a CRC algorithm. This is both slow to hash and resistant to collisions, and in which the hash is strongly salted using a long salt and a variable iteration count. Bonus points go to the incorporating a true vault mechanism with access control lists and leases, using a second authentication factor to FA or multi-factor authentication, and ensuring that there are strong logging and monitoring of access. Talk about race conditions logged under CWE 362. Race conditions occur when a sequence of actions occur during a transaction in a non-atomic manner, but an attacker is able to interrupt, reverse, insert, pause, or otherwise interfere with the expected execution order. For example, they give a scenario here where they receive a request for a refund, they check if it has been made, they send the refund, and they update the record that the refund has been done. There's a race condition in that there is a window, however short, in which the system may be willing to take multiple refunds since it's performing the processing on step 3 before completing step 4, meaning that it's going to check if the refund has already been made, and it's going to send it, and it's going to update that record. However, it's not updated yet, so while it's sending, you can still send in new refund requests, and it's going to check, has this been made? No, send another one. And then only after a little bit, the refund request is gonna be updated. So that is a race condition. For example, imagine the attacker sends 2 identical requests in very short order using a script. The system might receive and process these in the order as seen below, where as you can see it's going to check send 2 refunds because the check sees that it's not been made yet. Even though only 1 refund was due, the system has refunded double what the customer was due. Race conditions are often difficult to identify and reproduce due to the requirement to win the race. However, their impact can be quite severe. Preventing this vulnerability requires careful use of synchronization, i.e. mutex locking, and atomic actions to ensure that the state has not been changed between each step of the algorithm, but it's internal, quote unquote. The last example is one that highlights that sometimes a vulnerability doesn't have to be technically complex, and the developer or manager may be aware of the vulnerability existing, yet not considering it to be a vulnerability. One such example currently seen in web application is the concept of storage of sensitive data in a mechanism without access control. So meaning there's no login, there's no real access control put on it, but they think that since it's internal, it can't be hacked anyway. CWE 921. In which data is stored in a local data store such as Redis or Memcache, both systems in which no authentication is configured by default. So tip there, of course, put on authentication there. Can be either with the LDAP authentication, can be with a password username, can be OAuth2. There's many different ways that you can do authentication, but no authentication is never the right way. The developer may consider that no authentication or access control is required since the service is bound to localhost or the local network only and the port/server not exposed to the public internet. SSRF, anyone? It is therefore safe from attackers, right? Unfortunately, attackers love this kind of assumption since it permits them to weaponize or chain other vulnerabilities due to a lack of defense in depth. For example, if they achieve RCE on a completely unrelated host on the network, one which doesn't contain sensitive data, they can pivot that attack to access the host with a sensitive data store that lacks access control and trivially extract, delete, or modify its data. Or if the application has a SSRF vulnerability, it could be exploited to proxy access to the unauthenticated service bound to localhost. Preventing this issue requires that access to all services is carefully controlled using both authentication and authorization. It is then critical that the credentials used to access these services are stored securely, intentionally submitted by the application rather than being automatically included. Great article by AppCheck. Again, I'm going to link it in the description below because I would really recommend you check it out yourself and click through on all of these articles. If you want, maybe have a look at the how AppCheck can help you as well, or contact info@thexssrat.com because we also do pen testing and we also go far beyond just the regular Owasp top 10. Thank you very much for your time and attention, and I will see you in the next one, ladies and gentlemen. Bye bye.